What's up? Today, we're going to be implementing a queue. Well, first, let's read through the article, and then I'll start whipping some of this stuff up. One way is the way we can all probably think of, which is that you have a backing array, and then you have two indices. He calls these indices read and write, or like head or tail, or something like that. Start and end. Head and tail, like start and end, they get a little confusing if your indices start to wrap around the backing array. So I actually do kind of like the read and write terminology. I'll probably use that. And then instead of using the modulus operator, it's pretty interesting. This person's implementation masks. So you take the array capacity. Let's say you have a ring buffer with a backing storage of like 10 elements. So, yeah, 10, that's fine, 10 elements, right? So your capacity is going to be 10. But as in most languages, the max valid index is going to be capacity minus 1. So you take capacity minus 1. So maybe I shouldn't say 10, because one of the let's say 8, right? One of the things we'll see later on is that the author assumes for the final implementation, or actually requires for the final implementation, that the array size is a power of 2. So we'll call it 8, and that's going to be one set in the fourth position, starting from 1. And so if you have 8 minus 1 is 7, so in binary that's going to be like 0b111 essentially. Once the value, I guess for the mask checking this, like if you have an index indexing into the array and that value is counting up, it counts past 7 to 8. When you do the bitwise AND with 111, you chop off the top bit essentially, and so you will kind of wrap around. This is kind of something I would reach for pretty frequently without masking, just use modulus or something like that, just because it's like the very first thing that pops into my head. Second thing would be, well, there's an issue here, right? So like the issue is that like the downside of this representation is that you always waste one element in the array. If the array is 4 elements, the queue can hold at most 3. Why? Well, an empty buffer will have a read pointer that's equal to the write pointer, but a buffer with capacity n and size n would also have the read pointer equal to the write pointer. So you can see here when the buffer is empty, there's read and write equals 1, and then when the buffer is full, there's read and write equals 1. And the point is that you can't differentiate between empty and full cases. To address this, right, we could have the array, the backing storage, with an index into it plus a length, intermediary between a concurrent reader and writer. And so, yeah, if you have both reader and writer setting and checking the length all the time, then you might have some sort of synchronization penalty or something like that. We have a read and write member in the struct, and the masking is only done on push and shift, it looks like. And then so, yeah, to check if it's empty, you see if read's equal to write. To check if it's full, you just check the size of the backing storage, or excuse me, not the size of the backing storage, just the current used size, which would be your write pointer minus your read pointer. And then you check it against the backing storage capacity, basically. And I have to remember how to do all this in Jai, so we'll see. I'm already starting off with C. There we go. So it's going to be a struct, and in the struct, we're going to have, I'm going to, again, not be so much of a miser and have U64s here for, again, I'm writing C. I say U64, and write U64, and then our data, this is going to be an array. I'll hard code the type for now. I mentioned I'll make a generic later. So we'll just have an array of, I guess, U64s. The question is, how big does this need to be? We will, for now, we'll just put the data on the heap or in some sort of allocator. So we will have something like a ring buffer initialize, which will take in, it doesn't actually need to take in any ring buffer itself. We can just spit a ring buffer out. So we will take a buffer size, I guess, the size, which will be a U64. That's going to play into data here. It's going to determine how big the allocation is. And we would need to take in a type here in the generic case, but we're going to return to that. And this will return a pointer to ring buffer. The data is going to be on the heap. We need to make a new array. And I think there is a new array in Jai. Again, I'll have to look at the documentation off screen because I don't know if I can show that while it's in closed beta. And then we're going to have our b.data is So this will be default, read and write will be default initialized. They'll both be at 0. It is kind of interesting though that this read and writes are initialized at 1 here. I don't know if that's just for illustration purposes. I haven't actually thought about it that much, whether we can't initialize them at 0. I don't see why we could not, especially when checking for empty is just return read write. So I think we can set those to, I'm going to leave those as 0. So these will be default initialized to 0 when we create a ring buffer on the stack like this. For data, we could check the result of unaligned base. If that is null, then allocation has presumably failed, but I will just check if data.data is null. Just compile. It's not compiled because we wanted an S64, but I gave it, Jai deals with a lot of S64s for sizes. So we will, I guess, just cast this to S64 at the risk of misinterpreting this data. So here we go. I wanted bool, right, because we can't do this automatic conversion. So in the assert, we need to see if it is not equal to null. And I wanted a pointer to ring buffer. Right. We're not returning a pointer anymore. We're just returning a normal ring buffer. Okay. So that's that. And then in main, we will start doing some testing here. And we'll just ask for 10. We will have push and shift. And I guess you'll need ring buffer full. So ring buffer, we already know the ring buffer empty is simply going to be return. We do need a ring buffer here, right? So we don't need to modify the ring buffer. So we'll just take it as that. Return RB, RB.read is RB.write. This is masking here, and this takes a value. The value is going to be one of the indices, so it's going to be U64. So we're going to mask I, which is a U64, and that is, we take I, and we mask that. It's going to be the cast to U64 again, oh wait, right, we need to actually operate on the ring buffer. So we'll take RB, which will be we're going to be calling mask from push and shift, so might as well just consume pointer, because these guys are going to get a pointer. All right, might as well just do that now. In Jai, you don't need the arrow operator. This is going to be data.count. That's that. And then for pushing, well, first we want to make sure that it's not full. And for shifting, we want to make sure that it's not empty. So assert that we're not empty, the ring buffer. So our return value will be data read, and then we will advance read by 1, and then we will return ret. Right? Assert that we are not full. Full is going to take a ring buffer in here. V the value, read 64. Again, that'll be generic eventually, and then we say that the ring buffer data write is value, and rb.read, right. Okay, kind of all over the place here. I have to get back into this way of thinking. Advance that, and we don't need to return anything. Oh, right, the masking, right? That's what I'm forgetting, because right, in this case, right does not equal 1. Right equals 5. So for checking if we are full, this is going to be some operation against the RB data greater than or equal to, I guess. I'm going to have 5 minus 1 is 4. 4 is going to be equal to 4, and so we indeed are full. And in case right somehow ever advances past in increments yet even further, the greater than case should handle that as well. Was I thinking I was going to cast this or something? Why do I have parentheses around all these? Yes, we take I forgot the -1, right? I think I was just talking about that, and I still forgot it. We're actually using the indices to go into the array, so there's another bug there. I'm not finding these bugs, obviously, through testing. I'm finding them just through reading the blog post, but whatever, man. Right, so we need to actually mask this. Mask, right, and so same thing for the shift. We need to mask this as well. Size, I might change the name of that. It's a little bit confusing, I think, because like, is that the size of the entire backing storage? Is that how many elements are used? Maybe I'll call it used or something like this. I'm not sure. But this is going to be RB write minus RB read. And let's compile this and see what's going on here. So type one of ring buffer, type given pointer to ring buffer. Okay, so I need to figure out how to dereference in Jai. That's on line 24. I think that is it like this? Oh, here we are again. Okay. Number sign is mismatch. Right, RB data count, that's correct. There's probably, bug laden in this. I'll go think about this later. Either that or I'll just deal with S64s. I mean, I probably should. These actually, read and write probably actually should just be S64s. Well, actually, no, hold on. Wait, yeah, this would get me because we are relying on wraparound, and the bit masking won't matter that much, but we are relying on wraparound. Oh, also for initialize, I need to assert that we are power of 2. Yeah, for now, I guess we'll keep these as U64. That will compile. Okay, so now we need to run some tests, right? So ring buffer initialize. I already messed up by asking for number 10 elements, right? We said that we don't support that, so ring buffer initialize. We will need to assert here. I will make it invalid. I will make it invalid to request backing storage of size 0. Right? We'll have like bits per byte. I don't know how silly this is. Let's just play it out and see what happens. Bits per byte is going to be 8 bits per byte, and then we'll have num bits is size of type of size, preparing for it to be generic, right? No, size is never going to be generic. Size is never going to be generic. Size is always going to be 64. It might be an S64 later, in which case it would be a bug. Be a logic bug to say U64 here, although that would be transparent to us because it would give us the same result. Time bits per byte. Okay. For 0 to num bits, it's inclusive in Jai, so we have to do that, right? So num bits is going to be like, it's going to be 8 times 8, which is 64. So we're going to loop from 0 to 63. And then what we do here is we test each individual bit. Size must be a power of 2. Okay, 8 is a power of 2. So what have I done wrong here? Of course, okay, obviously. all right. There we go. What am I talking about, right? Okay, so stupid simple mistakes, but obviously we don't want to adjust size only in the case where a bit was set. We want to adjust size every single time. We just want to trim it down. All right, here's a naive way to like brute force this without doing any bit twiddling. Right, do some test cases now. All right, so we start the third being the full. I'm actually going to go to 2, so I don't have to push so many things. So I want to trip it and just see what happens. Okay, so here, all right, so actually, yeah. All right, that's clearly not what I want. I don't want file path. I think there's probably something in location, like file name or something. Okay, so I need to change a bunch of code in my game code. This is going to be fully path file name. Ring buffer push, and we're going to push to RB, and we're going to push a 1, I guess. Assert that it's not empty, right, not empty, and assert that it is full. So the last thing I need to do is actually rotate the indices. And in order to do that, I need to, well, yeah, we also need to test shift. So we'll shift off. Let's see where read and write. Read and write would point now. They start at 0. You push twice, so 1, 2. So it points at 2 now. So mask is already going to come into play. We will assert b equals 1, assert b equals 2, run that. Okay, assertion failed on 72. That's interesting. Okay, wait, maybe mask is broken or something? Let's break that push, which would be 66. 66, and we'll run this. Okay, so see where we are here, right? If I print 0, that is 0. That's most interesting. I'm on line 67. Okay, why is that 0? I guess we can step into mask and see what mask is doing. Actually, let's make this a little bit easier on ourselves by just doing this, right? It's a little bit easier to debug. This guy, go back in the GDB. We will break on 69. So here we are. Now we're at V. So print V, that is uninitialized because we just entered the scope. So if I go next, print V is, okay, all right, so that's what's going on. I'm not getting a seg fault, right? So V, this is what's going on. We're getting back a crazy index. Right. The problem is so obvious now. It's precedence again. All right, still learning. I could be tripping now, but I could have sworn that I had parentheses here. Like they were like wrapping the whole expression though, right? And I was like, why do I have those? So that was also incorrect, but okay, that's obviously needs to happen here. I just run main. Yeah, it just works. Okay, great. And now what we need to do is just push one more thing on there. And okay, that's that. Great. So we have a working ring buffer after a bunch of silly mistakes. So in the case of 8, you have 1, 0, 0, 0. That would be number. And then number minus 1 would be 7, which would be 1, 1, 1. So you have 1, 0, 0, 0, and you have 1, 1, 1. And that's the case where only one bit is set. And so you have 1, 0, 0, 0, and 0, 1, 1, 1, which is going to be 0. So 0 equals 0. Therefore, only one bit is set. If you have, let's say, if you have the number 3, right, it's going to be 1, 1, and then you minus this is going to be 2, it's going to be 1, 0. So 1, 1, logical and with, or bitwise and, excuse me, with 1, 0, you are going to have the 1 in the second position, or rather the first position from the right, both set in both those numbers, so that's not going to be equal to 0. Okay, so that's a lot more beautiful than this, right? Okay, sounds good. Get rid of all this stuff. This should still work as is, and it does. So now the next thing I'm going to do before I wrap this up is we're going to make this generic. The $ means we must know the value of t at compile time to call the procedure. So this guy here is going to take a type, right? It's going to take this is going to be a type. And instead of like this U64 here, we're going to have a new array of this many size of t. Oh, polymorphic structs. Here we go. I totally missed that. 120. I read 120 as polymorphic procedures. It's 100 polymorphic procedures. 120 polymorphic structs. Just like procedures, struct declarations can have argument lists. These arguments can be used inside the body of the struct to determine types and values of the struct's members. But since this is a statically typed, fully compiled programming language, all these decisions about the struct's members are made at compile time because that is what allows programs to run efficiently. At compile time, the compiler bakes these struct declarations down into structs that have no more parameters. $n, and this would be like size or something like that, right? Size. And so it looks like this, size t, okay? So data is size number of elements with element type of t. It would be RB is ring buffer, which would be the size, no, it would be the type, so U64, and then the number of elements. This now gives us a ring buffer on the stack. And that is, I think that's actually what we want. This actually is good. This allows us to have it on the stack. There's no constructors in this language as far as I know. There will be initializers. So we don't actually have a way to enforce our invariant on size here. So in fact, we will get rid of this because we do want to enforce the invariant. This returns a ring buffer of, I mean, how do I even annotate this? T? Like that? I think like that. And then this ring buffer here would be T. 264. So we assert that size is greater than 0, and we also assert that we have a power of 2. And now we create a ring buffer on the stack, which is just going to essentially be 8, 16, 32, because data is going to be a pointer, which is 8 bytes, and it's also going to be an S64 count, which is 8 bytes. Now, how do we take this in as an argument? I do need to figure out the difference between $t and not $t, right? We did read that $t requires a compiler to know the type at compile time, but like, when do I need to use that? We'll figure it out. Let's look at the implementation of this stuff in hash table. They're not using $ for the types in the declaration of the struct, right? So like, makes me think I can just like get rid of that. Wait a second, the actual memory outline of ring buffer, given the way that I'm parameterizing the types is independent of the types that I ask for. Because remember, data, the array, is just a pointer and a count. So maybe we don't need like a generic representation for the return type of ring buffer. Like I want a way to constrain the type of this v based on the type of the ring buffer. And like, I don't know how to do that. However, because struct parameters are all supplied at compile time, there is no possibility that they are non-constant. So the $ is superfluous, and we can simply choose not to write it. Okay, that's why the $ is missing in the type definition of these structs here. It's very common to write procedures that take any polymorph of a struct and operate on those generally. For example, there's a holder, do indices match, hold. Okay, this is how we do it. Okay, well, let's just give it a whirl, right? So here, it looks like we do this, right? This is actually parameterized with a $, and that probably has to do with the auto bake thingy, which I didn't read. And so I'm thinking I can do that, right? It's a ring buffer of type T, and I want to push in a value V here. The cool thing about Jai, by the way, is for performance reasons, if this is big enough on, if this would be large enough on the stack, or excessively large, Jai will make a determination to convert this to a pointer for us. So tell me what I did wrong. All right, at the end of compilation, this procedure is still polymorphic. Because this is a statically typed programming language, all polymorphism must be resolved before you can use the procedure in compiled code. This is initialize, okay. Is it the case that I actually might need to parameterize this? Yes, that was it. And we're going to take this guy here and boom. And we know about types now. So we have a T, which is a type, and we are going to do we're going to do 2 of those and pass in the type here. Test with type. Test with type, we did a U64 earlier, and then test with type. Well, okay, so I'm doing numeric comparison here, so I guess we'll just do S16 or something. That should be fine, right? Then do this. Oh no! Okay. Declaration is ring buffer initialized. The declaration of argument 2 requires a value bake. It is declared with a $ before the identifier. But this expression is not a bakeable literal. It is a type. What if I just do this? What if I just like cheese this? No. Oh, it requires a value bake, right? Which is something special that I don't know about yet. So let's go read about value bakes really quick. Auto bakes, 115. In 100 polymorphic procedures, we saw how to define procedures that look like blah, 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 which means that X can be of any type T, and T gets baked into the procedure at calling time, which is one primary way we make procedures that adapt to arguments of varying types. But we can also use $ not just to bake types, but also values. This looks like this. Okay, the $ comes before the parameter identifier, not the type. The $ is in front of the variable rather than the type. We'll work through some scenarios involving how this may be useful. Okay, so let me read this again. The $ before the type means that the parameter can be of any type T, and T gets baked into the procedure at calling time. Okay, so T gets baked into the procedure at calling time. So is it the case that if I comment this out, that it just works? No. Wait, okay, yeah, what if I value bake that? Is that what it's talking about? That's what it's talking about. Okay. And so why did this work, right? Test with type. I was passing in T, which was not polymorphic, right? It was not generic. It was a literal type. It was not an auto bake, I guess is what they call it. I don't have to read more of the docs. No, I have talked myself into confusion. So I need to read more of the documentation before I explain why that worked. It just worked. Right, compiling works, running it works. That's U64, that's S16. I could extend these, so we could have like a custom type, right? We could have like a struct, we could have like foo, which is a struct, which has like a int, b, int, and then we could have like operator, and this would take like a foo, would take like a foo and a b foo. And I would return a dot a equals a dot b dot a and b dot a equals, nope, a dot b equals b dot b, something like this, right? Does that compile? Too many return values? Wanted 0, right. Because this returns a bool. And indeed, okay, so that's how you overload the operator in Jai. And then I would have to rewrite some of this stuff just to do the checks here, the asserts, and also the pushes. I mean, I feel like it's kind of worth it. We'll just hard code this really quick. F3, assert is F3. That builds and it runs and it passes. All right, there we go. So we now have a type generic ring buffer. And my intent is really to use this as a queue in pathfinding algorithms and whatnot. But there it is. Well, we'll catch you then.